This is a quick overview of what retrograde motion is. We're looking at just part of the sky here. This is the constellation of, or part of the constellation of Iolcos, the serpent bearer, which is just north of the constellation Scorpius. This is its brightest star, Antares. This one here is a globular cluster. And once I hit the forward button, we will see planets moving from right to left, which is west to east. And we also will see Saturn come by, and Saturn will be in retrograde motion. So here we go. And there's Saturn, and all of a sudden it is moving left to right, east to west. We see all the other planets come by here. The Sun is very prominent. There it is, and that was Mars, and I think Jupiter is coming up. There it is. And so all planets are pretty much, and there it comes back actually. So planets are moving west to east in their orbit, but about once a year, usually once a year, they're moving in the opposite direction, or so it seems. Okay, so here's what actually happens. We're now looking at a top view of the solar system, and in order to fit that in here and not to have too much commotion going on, I only have the Earth's orbit and Jupiter's orbit prominently displayed. Saturn's orbit is actually over here. You can see it in the corners, but if I try to squeeze Saturn's orbit in here, then Earth's orbit would be too small, and that's not what I want. So I'm just looking at Earth and Jupiter for now. I'm going to hit the forward button here starting in January of 2014, and we're going to look at this one every 2 days, and we can see that both planets move nicely forward. I also have the tracking turned on, so we can see that Earth in the same amount of time moves much faster and much further than Jupiter. That makes sense because Jupiter is in an orbit that is further out, so it will take it more time to orbit. It is also slower in its orbit. In any case, the two are nicely moving, and I'm actually a little bit too far. I'm already in 2016. I want to go all the way back to actually 2015. I have kind of trouble hitting the stop button here. There we go. Okay, January 2015, and I'm going to aim for January 2016 actually, so I hope I can do that. Okay, I'm a little bit too far. Okay, so the two are orbiting nicely, so do the other planets, orbiting nicely in this counterclockwise orbit around the Sun. But then when Earth moves in on Jupiter, it seems like, and of course we're only observing Jupiter and any of the planets from Earth itself, it seems like that Jupiter moves backwards. This is really tough to see here. That's why I have to go to the other screen in a moment. So even though Jupiter is moving forward from Earth, because we overtake Jupiter, it seems like Jupiter is moving backwards. And I try to aim for January 2016 because that's when Jupiter's retrograde motion starts in that year, and then it completes itself in May of 2016. I don't think I'll be able to do that because, oh, there we go. So here Earth has moved far enough ahead that as we're looking at Jupiter in this line of sight, that Jupiter again moves forward just like it should. And again, the whole thing is just the way it appears from Earth. So now I'm going to go back to the other setting I had earlier, and I'm going to move this over here. And again, we can see Antares and that globular cluster there. And I'm going to move forward 1 day at a time, and there's Saturn retrograding. And now I'm going to switch to Jupiter, and I start this with in early September of 2015. Okay, Jupiter's just out of the picture, and I want to get the sun out of here. There we go. Okay, so there's Jupiter actually coming into the picture. And as I go forward here, so Jupiter moves right to left just like it should, just as it should, and we are following it. We're faster. Because we're faster, at some point we're overtaking Jupiter. We can see there was a moon a moment ago, and Mars enters the picture, and so does Venus. Okay, and then I should probably move that over here. Okay, I'm now in October of 2015, and then my screen is just a little bit too far. I'm now in November, and I'm still a little bit too far. And I know what happened. I meant to change the zoom factor. There, that's better. Okay, I've got it back on the screen. And so this is November 2015, December, January coming up, and right there, this is where Jupiter seems to stop and move actually backwards, retrograde. This is just an optical illusion that is produced by Earth starting to overtake Jupiter, and from our location on Earth, it looks like Jupiter is moving backwards, retrogrades, but it only looks like that. Jupiter at all times is actually moving forward, which is right to left, and it only appears from our view. Now Jupiter regains its motion. This is called prograde. Only from our point of view, because we're overtaking Jupiter in our own orbit, it looks like that, as if it was moving backwards. So that's retrograde motion. It's a little bit hard to explain. At least you have an animation. In astronomy books, you just find drawings, and with an animation it's at least a little bit better to explain. By the way, there's Mercury, and Mercury also retrogrades. Alright, that's good enough. So here's what I use retrograde motion for. I determine the distance to the outer planets by observing the retrograde motion. So here's the diagram. This is obviously Earth's orbit, and again we see here the tracking of Earth along its orbit. And here is part of Jupiter's orbit. So obviously, and again here there's a tracking of Jupiter in the same amount of time, and obviously I zoomed in, so we only see part of Jupiter's orbit here, so that I can actually show the geometry. I'm going to explain the geometry. This little triangle here describes the baseline B that we have here, and the distance from Earth to Sun here and here, and the one that you see there means that the distance is considered 1, as in 1 astronomical unit, and that is the astronomical unit is the standard distance within the solar system. It's 93 million miles, or 150 million kilometers long, and it just makes it, just using that 1 astronomical unit makes it a whole lot easier to talk about distances in the solar system, so that we don't have to talk about millions of miles, but we can just say, well, that planet is 5.3 astronomical units away, or 30 astronomical units away, and then we know it's 30 times as much as the Earth. In any case, those are the distances we want to get for Jupiter and Saturn. So in any case, here's this little triangle here, and then here's this other triangle. So this one here, Earth is looking at Jupiter, and then at the end of retrograde motion, Earth is also a Jupiter, as if Jupiter was in the same spot. Of course, Jupiter is moving, but in order to show the geometry, I assume just for a moment that Jupiter is stationary here so that we can actually get these triangles. This triangle over here will produce a side F, which I didn't put in here because it's just too small here. And when you look at that triangle, that looks like the law of cosines. And then we have this other triangle here where we will calculate the distance E, the height E of this triangle. And again, you can see that this is probably going to be the law of cosines. The total distance E here and F, again, F is actually not shown here, then is the distance from the Sun to Jupiter, and that's what we're aiming for, and later then the same thing for Saturn. The things that are being measured is the time it takes for retrograde motion, so this time here, the number of days, and how much retrograde motion appears, and that is that angle alpha 2. At the same time though, Jupiter is moving forward in its orbit. That's this little angle mu here, and that will be then added to alpha 2. Okay, let's go through the algebra here. There's a lot of explanation here that you can see in the posted Word doc. This is that little triangle that we saw on the left. Here's the law of cosines. I think you can see it easily here. The 1 squared is in here because 2 of the sides are 1 AU long. Then this one here is the large triangle, also the law of cosines. Then put the two together right here, and we come up with this expression. When you look at the Word doc, you can look at the algebra. It's really simple. You can almost see it right here, what's happening. So that will give us the side D of the large triangle. Then we have to make a correction because the planet moves itself. So we have to add the angle mu, which gives us then alpha 2 plus mu is the angle epsilon, which is right here. So that's why the formula actually changes. I explained it a couple of minutes ago. And then finally, with the Pythagorean, we come up with the height of each of the triangles, E and F, which we then add, and that's the total distance of the planet to the Sun, which is what we're aiming for. Okay, now these are the data that we have to plug in and calculate. Basically, there are only two things that I looked up for each of the planets. One is when they start retrograding right here, so January 8th, 2016. If you looked really closely earlier in the animation that I did in the astronomy software, you can actually see that at what date that started. And then here May 10th of the same year is when it stopped, and so that's the number of days I determined, 123 days. Notice that for Saturn, these are the given dates, it takes a little longer. That's typical. The further out the planet is, the longer retrograde motion takes. That's because the planets further out are slower. For Mars, in fact, which is closer, it actually takes only about 70 days. Okay, then I'll scroll a little down here, and we're going to calculate the data in just a moment for Jupiter. This is the other thing that I measured. I also did that in that astronomy software, 10.0 degrees from one end of its retrograde motion to the other end. So these 10.0 degrees that Jupiter moved from left to right in, or seems to move, that is actually only what we observed from Earth, that optical illusion, as if Jupiter was moving 10.0 degrees to the right. Saturn moved 7.1 to the right. Again, that's only our optical illusion as apparent retrograde motion, from which we will determine the distance. And then here, these are the angle that you saw on the diagram, the sides D, E, and so on. I think side F is right there. And then eventually we're going to come up with a total distance of planet to the Sun, which we then compare to, these would be the average one here for Jupiter, and because it is slightly elliptical orbit, that's why in the observation year that I chose here, 2016, it's a little bit further out. Similar here for Saturn, 9.58, and during the observation year that's actually a little further out again. And I'm going to do all the numbers here for Jupiter, while it is your task to do the ones for Saturn. Alright, let's get started here with the calculations. By the way, these numbers here, these dates and these numbers here, these measurements, they are taken off in astronomy software, which is a convenient way of doing this here, but of course it could be real observations, observing the planets and coming up with the same data and doing the same calculations. Okay, now finally let's get started. First thing I'm going to do is I determine the angle that Earth is moving through in 123 days. So that's the angle for the little triangle. So 123 days divided by 365 days should be 365.25, but I will only have 2 or 3 sig fig. I think I have 3 sig fig anyway, so 121. This one here. Okay, now I'm going to calculate the side B. That's back to the diagram, this one here, so that takes the law of cosines. I just have alpha 1, which I believe was 121 degrees, and it looks like an oblique triangle, and it is. Here's the equation. So I'm going to get B by doing this one here on the calculator. So square root of 2 times 1 minus cosine of 121 degrees. Okay, 1.74. There we go. Okay, side F. And I'm going to go back here. So side F is, or the height F actually it should be called, is this little piece that is not labeled in the diagram because it just would be too much for the diagram. And side F is simply the Pythagorean. There it is. There we go. So square root of 1 squared minus parentheses 0.5. Of course I didn't write the square here because 1 squared is 1. So 0.5 times the 1.74 I had a moment ago, square, oops, first close the parentheses, then square that, parentheses for the square root, enter 0.49. So the height of that triangle is 0.49 astronomical units. There we go. Okay, this is the angle that I measured in the software, so that's the angle by which Jupiter seemingly retrogrades. Now here I'm going to calculate that at the same time it's also orbiting through a certain angle, and that needs to be added, so it is the 123 days. Actually, I can do this. The formula is almost the same as the very first one I used, this one here, except I have to divide by Jupiter's period, which is the time of 11.86 years that it takes to orbit the Sun, and that will tell me the angle that it moves through during that amount of time, so 10.2 degrees. And now I add these two here, so actually my angle for a triangle is 20.2 degrees as I add these two numbers. Okay, then I calculate side D. So here's the equation for side D. There it is. And again, the algebra, when you look at the Word doc, should be really straightforward. I think you can see that easily, how I ended up with this expression. Alright, it's going to clear this out a little bit. So, square root of, open another parentheses for the numerator, 1 minus cosine of the angle alpha 1, which is 121 degrees. Close the cosine, close the numerator, divide. Open the denominator, 1 minus cosine of the 20.2 degrees I had a moment ago. Close the cosine, close the denominator, close the square root. There we go. Enter. 4.96 astronomical units is the side D. 4.96. Side E is using the Pythagorean. So that's the distance from the baseline all the way out to Jupiter. So a moment ago I calculated side D here with that. Oops, it's just out of picture, sorry. So a moment ago I calculated side D here, which was that complicated square root equation with the cosines. Now from that I used the simple Pythagorean to get E, and then the last thing I'm going to do is I add that to that F here, and that gives me the total distance. Again, the F is only not in the diagram because I just didn't know how to fit it in here. It would have been just too overwhelming, or maybe not. Okay, here's the equation for it. E, simple Pythagorean, as I said. There it is. Plug in the numbers, so square root of d squared, I just calculated d squared, and still on the screen, of 4.96 squared minus parentheses 0.5 times the b square I had earlier, that was 1.74 parentheses squared, and the parentheses is here for the square root. Enter. So E is 4.88. There it is. 4.88. And the total distance to the Sun is at the sides, or they actually should be called heights, E and F of the two triangles. F is here 0.49. 0.49 plus 4.88, I can do it in my head, 5.37. And that 5.37, the total distance of the planet to the Sun, I compared to distance listed in astronomy textbooks, which is the average distance, 5.20, pretty close. And for that particular observation year of 2016, I also looked that up. It's 5.41, so you can see I'm really close to that one. So that is less than a 1% error. Alright, so now it's your turn to do the same thing for Saturn. So diagram here applies exactly to Saturn as well. The only data that you need are the ones that I grabbed from the software. When it starts retrograde motion, when it completes retrograde motion, and these are a number of days I come up with, and then I measured the angle of that large triangle, 7.1 degrees, directly on the screen. And when you go through the calculations, you come up with one number after another. Eventually you're going to come up with the total distance of the planet to the Sun, and then you're going to compare that to the average distance as well as to the distance during the observation year. I did that myself, just as a hint here. This one is going to be a little bit further off than these two compared. This is really precise, less than 1%. Here you're going to come up with about a 5% error. So kind of look in the neighborhood of like either 9.5 or 10.5 AU, one of the two numbers, and that would be about the correct result.